Hello, welcome to video 2 in the section on numerical methods. And in this video, I'm going to discuss estimating the error incurred when we use either the Trapezium rule or Simpson's rule to approximate a definite integral. And so the basic fact is that the error in the Trapezium rule, that's the absolute value of the difference between the actual definite integral and the approximation that we get from the Trapezium rule, is proportional to h squared. Remember, h is the width of the intervals that we use when we divide up the interval from a to b into subintervals. And so as h gets smaller, this gets smaller. And so one thing to note is that we normally taking h to be a small number, less than 1. And so when we square h squared is smaller than h. So having the error of h squared, or proportional to h squared, is better than having error proportional to h. And similarly for Simpson's rule, the Simpson's rule is generally better than the Trapezium rule. The error is proportional to h to the fourth. And so that's much smaller than the error for the Trapezium rule in general. If we have a small number, its fourth power is much smaller than the second power. So for example, if h is 10 to the negative 2, 1 over 100, then h squared is 10 to the negative fourth, that's 1 over 10,000, and h to the fourth is 10 to the negative eighth. Now let's look at an example comparing the error in the Simpsons and Trapezium rule when we use it to approximate this integral, the definite integral of sine of x from 0 to pi. Of course, we know the exact value of that integral, it's 2, but the point here is that we can see how accurate the approximations are. Since we know the exact value, we can actually see exactly what the size of the error is. And the thing that we should notice here is the comparison between the error in the Trapezium rule and the Simpson's rule. So in the Trapezium rule, when we use n equal 20 subintervals, and so that means each subinterval would be 2 divided by 20, or 1/10, 0.1 would be h. And the error in Simpson's rule is about 1/100th. That's something like 0.1 squared, proportional to 0.1 squared. And the error in the Simpson's rule is something like 1/10,000th, like 1/10 to the negative fourth. And so here we, roughly speaking, have h equal 10 to the negative 1. This approximate size of the error in the Trapezium rule is 10 to the negative 2, and the approximate size of the error in the Simpsons rule is 10 to the negative fourth. And so we see this behavior in the error in this example. Let's look at one more example, this time where we don't know the exact integral. So we'll estimate the definite integral of e to the negative x squared from 0 to 1. We use 10 intervals and also some other values of n. We can do many different possibilities by using a computer. And so if we want to do n equal 10, we need to calculate the values of the integrand, that's e to the negative x squared, at the end points of all the intervals. And so that's 0, 0.1, 0.2, and so on. So dividing the interval from 0 to 1 up into 10 subintervals. And we calculate the values of y, and then we use either the formula for the Trapezium rule or Simpson's rule in order to get the approximation of the definite integral. And, well, we've done it actually for a few values of n here. So n equals 10 using these particular values as shown here, but also n equal 4 and 20. And an important question is, how do we know, since we don't know the exact value of this integral, how do we know how large n needs to be in order to get a certain error in our approximation? So in order to approximate the definite integral to within a certain error, well, a simple way to do this is to increase n and see what happens. So when you increase n in a certain number of the digits and your approximation don't change, you can be pretty sure that those were correct. So for example here, we have in the Trapezium rule, between the approximation with n equal 4 and the approximation with n equal 10, the 0.74 stays the same. So we would guess that those are probably correct. And actually, in the next step of the Trapezium rule, it's just the first 3 digits that stay the same, so we might guess that these are correct. Looking similarly at this Simpson's rule, we see that between n equal 4 and n equal 10, the first 4 digits are the same, and they actually agree with the first 3 digits that were staying the same in the trapezium rule, and then between the n equal 10 and n equal 20, we have the first 6 digits are the same. So we might guess that those are correct. This isn't an exact way of being sure they're correct, but it's a way to check, reassure yourself that those digits are correct. If we then increase n to 50, we can see that we get a few more digits which are not changing as we're increasing n. So by adjusting n, you can estimate the size of the error. And this is actually there's more systematic ways to do this, but this is one method of estimating the size of error that you've made in your approximation, increasing n a certain amount, and seeing how that changes the result. We can also be more precise, and that's what I'm going to describe now. So the basic question we want to address here is, if we want a certain level of accuracy in our approximation, how large should we choose n? So that is, how many subintervals should we choose? And so, as we've already said, in the trapezium rule, the error is proportional to h squared, and the Simpsons rule, h to the 4th. If we want to be more precise, and to get an estimate that we can actually use to say how large n should be for a given error, we need some kind of estimate for how large the error is. And these estimates are shown here. So there's one for the trapezium rule and one for the Simpsons rule. And what they both say is that the error is bounded by this quantity on the right. So b and a are the two limits in the integral. The definite integral is from a to b. These numbers m2 in the estimate for the trapezium rule and m4 in the estimate for the Simpsons rule are related to the maximum value of the derivatives of the integrand. So f is the integrand. m2 is the maximum value of the second derivative of the integrand on the interval that you're integrating. And m4 is the maximum value of the fourth derivative of the integrand on the interval that you're integrating. And so if we can calculate those maximum values, m2 and m4, then we can get an estimate for how large the error can be. And if we make sure that these estimates are less than the error that we're looking for, we can then figure out how small h should be and how large n should be. Right? And so the thing that might hold us up here is calculating these maximum values. But if you can figure out a maximum value for the second or fourth derivative, depending on if you're using Simpsons or trapezium rule, then you can choose h in such a way to be sure that you'll get an error less than a certain amount. Let's look at an example of doing this. This can actually be pretty complicated if you want to do it rigorously, find those maximum values. But what it is in the end is just finding the maximum values of some derivatives of the integrand. So let's do that in this example. Calculate this definite integral, the same one we were looking at in the previous example. The definite integral from 0 to 1 of e to the negative x squared, accurate to within error of 10 to the negative 5th. And so we want to know how large should we choose n, how many subintervals should we use in order to get this error when using either the trapezium rule or Simpsons rule. So remind you what the errors are. So what we're going to do here is we're going to calculate the m2 or m4, and then make sure that these bounds on the size of the error are less than 10 to the negative 5th in both cases. And that will show us how small h should be and how large, therefore how large n should be. All right, so we need to calculate m2 and m4. And these are the maximum values of the second and fourth derivatives, remember. So m2 and m4. All right, and so in order to do that, we want to calculate derivatives. The integrand, in this case, f of x, was e to the negative x squared. The derivative. So a lot of this is just calculating the derivatives, the higher derivatives of this function. So the first derivative is negative 2x e to the negative x squared, using the chain rule. And second derivative, we need to use the product and chain rule. So we get negative 2 e to the negative x squared plus 4x e to the negative x squared. And let's see, we could combine those together and factor out 2. So that's 4x squared, 2 times 2x squared minus 1 e to the negative x squared. Okay, so up to the second derivative is not too hard. Actually, it gets a bit technical once we start calculating the higher derivatives. So to find m2, we want to find the maximum value of this function, the second derivative, on the interval from 0 to 1. So let's do that. And actually, it's the maximum value of the absolute value, the modulus of this function. And so the maximum of the modulus of the second derivative must occur either at an endpoint of the interval. So the endpoints are 0 and 1, or a point where the third derivative is equal to 0. So that's the derivative of the second derivative. The third derivative is equal to 0. All right, so we can easily calculate the values of this at the two endpoints, 0 and 1, but we should also check that there are no points inside the interval from 0 to 1 where the third derivative is equal to 0. So let's calculate the third derivative. We have to calculate that anyway in order to get to the fourth derivative for m4. So let's calculate the third derivative. You have to use the product rule again in the chain rule. So let's see, we have 2 times 4x. Let me check the derivative of the 2x squared minus 1. Minus 4x times 2x squared minus 1 e to the negative x squared. And okay, let's try to simplify that. There's 4x in both terms, so we factor the 4x out. 4x. Also factor the e to the negative x squared out, which occurs in both terms, and we're left with here 2. And then there's a plus 1, so that's going to be 3. And then minus 2x squared. And e to the negative x squared. Okay, so that's the third derivative. And, well, we want to find where it's zeroed in order to find points where the second derivative might be maximum. And so let's check where that would be 0. This is equal to 0 when x is equal to 0. Right, so that if this x here is 0, or this 3 minus 2x squared is 0, and that happens when x is either plus or minus the square root of 3/2. Okay, so the points where the third derivative are 0 are x equals 0 and plus or minus the square root of 3/2. Now the square root of 3/2 is not in the interval from 0 to 1 where we're integrating, so we don't have to check these ones to see if they're maximum. So the only points where the maximum could occur of the second derivative are the points 0 and 1. And so let's check the value of second derivative at those 2 points. So the second derivative, the formula is here at 0 is 2, negative 2 actually, but we're checking x at the modulus, so 2. And the modulus of the second derivative when x equals 1. We get, this is 1, so 2, and then e to the negative 1. So 2 divided by e. Right, so the maximum value occurs when x is equal to 0. 2 is the maximum. Thus, m2 is the maximum value of the second derivative x on the interval. So for x in the interval from 0 to 1 is equal to 2 in this case. Okay, so this is the value of m2. Now, in this case, it is possible to calculate m4 explicitly. You have to calculate the third and fourth and then actually fifth derivatives, because we need to check for the possible points where the fourth derivative could have a maximum. And this is actually quite a technical calculation. If you want a challenge, then I suggest you should try it and try to actually work out this, but you do it, if you work through this, m4 is equal to 12. You find m4 is equal to 12. That's the maximum value of the fourth derivative. So just to remember, maximum value of the fourth derivative f for x in this interval. All right, and so now let's use those in the estimates. And so maybe we should quickly switch back and remember what the estimates were. So here they are. So m2 was equal to 2. And so in the estimate for the trapezium error, the trapezium rule error, we're going to have b minus a times 2 divided by 12, and b and a are 1 and 0. So this is just 1/6 h squared. And in Simpson's rule, we have 1, b minus a is 1, and m4 was 12, so 12 divided by 180 is 1/15th. And so 1/15th times h to the fourth is the estimate of the error in Simpson's rule. All right, and so let's switch back and look at what that says then about the number of intervals we should use. All right, so using those error estimates and the values of m2 and m4 we just found, so the error in the trapezium rule is less than or equal to b minus a, again was 1 minus 0. M2 was 2 divided by 12 times h squared. Right? And we want that to be less than or equal to 10 to the negative fifth. Right? We want the error to be less than or equal to 10 to the negative fifth. That's what it says in the problem. That's the size of error we want. So this is the size of error we're looking for. Okay, and so we can see how small h has to be in order to get that. So I'd have to have h less than or equal to the square root of 6. Right, that's multiply 6 to the other side and take the square root times 10 to the negative 5/2. And this is approximately, I've worked it out here, approximately 0.007746, rounding to 4 significant figures. All right, so h has to be less than or equal to this number in order to get the size of error we want in the trapezium rule. Now let's look at Simpson's rule. So Simpson's rule. The error estimate, so once again, we had the b minus a here, that's 1 minus 0, and it was so 12 was m4 divided by 180, has to be, well, times h to the fourth, and we want that to be less than 10 to the negative fifth. All right, and so we want then h to be less than or equal to 15 to the 1/4 times 10 to the negative 5/4, and that's approximately 0.1107. Right, so in order to get this error less than or equal to 10 to the negative fifth in the trapezium rule, we need h less than this number. In order to get the error less than 10 to the negative fifth in Simpson's rule, we need error less than this number. And so what is the number of intervals we should use actually? So recall n, the number of intervals, is 1 over h. I guess I should just say it's equal 1 over h. And so we can figure out what n should be based on these. So the n has to be, so first maybe a trapezium. Trapezium rule, n has to be greater than or equal to 1 over this value, which is the maximum value of h that we can use. So it has to be greater than or equal to 1 over 0.007746. And that's approximately 129. n has to be an integer, so to round to an integer here. For Simpson's rule, n has to be greater than or equal to 1 over 0.1107, which is approximately 9. So for Simpson's rule, n has to be greater than or equal to 9. And remember, in Simpson's rule, n has to be even. So the smallest value of n you could use actually would be n equal 10. So remember, in Simpson's rule, we have to choose n even. So you can see you need much fewer intervals in Simpson's rule in this case in order to get an approximation accurate to 10 to the negative fifth. We need only 10 subintervals whereas we need 129, the trapezium rule. Okay, well, this is the end of this section. In the next section, we're going to continue and look at a different type of numerical methods for solving equations.